Welcome to Pomodoro Joe for Monday, June 26th, 2023. Today we're doing LeetCode problem 2462, total cost to hire K workers. This is a medium problem. You are given a zero-indexed integer array, costs, where costs index I is the cost of hiring the ith worker. You are also given two integers, K and candidates. We want to hire exactly K workers according to the following rules. You will run K sessions and hire exactly one worker in each session. In each hiring session, choose the worker with the lowest cost from either the first candidate's workers or the last candidate's number of workers. Break any ties by the smaller index. For example, and then they give some examples. All right, if there are fewer than candidates' workers remaining, choose the worker with the lowest cost among the remaining workers. Break the tie by the smallest index. A worker can only be chosen once. Return the total cost to hire exactly K workers. Okay, so in this problem, we are given three pieces of information. We have a list of, these are costs essentially, how much it's going to cost to hire a worker at that index. We have K, which is the number of workers we want to hire. And then we have candidates, which represents the number of workers in the pool, but it's sort of half the number of the workers in the pool. This candidates number is a number that applies to both the beginning and the end of our array. So we can choose any candidate within the first four candidates here, or within the last four candidates. So we actually have a pool of 8 candidates, 4 from the left and 4 from the right. We choose the cheapest worker from that pool of 8, and then we move on. But once we choose that worker, now we no longer have that worker in this list, so we need to shift a new worker into that area. So for example, we have 17, 12, 10, 2, 7, 2, 11, 20, 8. There are 4 candidates from the beginning, so that's 17, 12, 10, and 2. And there are 4 candidates at the end, that's 2, 11, 20, and 8, that we can choose from. Now of these candidates, the 2s are the cheapest, but we always break a tie by choosing the one with the lower index. So we choose this 2 as our first candidate, or our first employee. So that 2. Once we've chosen that 2, we only have 3 workers at the beginning, but we pop this 2 out of our list. So that shifts this 7 into the spot where this 2 used to be. So we have to shift that 7 in there. All right, so let's get started. Let's put 25 minutes on the Pomodoro timer, and we will start now. So for this one, we will have some result. So I'll have result equals 0 to start with, and we will return the result at the end. All right, so the first thing that comes to mind here is I'm always choosing the lowest value or the cheapest worker I can. So the lowest cost, that's the minimum value. Now there are different ways we can calculate minimum values, or we can find minimum values. Now if this were just an array of random numbers and we only had to find the value once, one minimum value, we could just go through every element in the array, find the smallest value, and pull that out. But that's not exactly what we're doing here. We're actually pulling out some subset of our array, the front and the end, so that's the left and the right. We're choosing the smallest between all the elements of those two subsets. Once we've chosen the element, we'll actually be adding new elements to the subset where we chose the element from, so we're going to be rearranging that subset. So that's more complicated than a simple linear search. We could sort our elements. That also gives us the smallest at the very beginning of our element list. If we sorted first, then we can pull the first element out. But that's going to be an expensive computation to sort our arrays every single time we go through. This problem is actually a very good fit for something called a heap. Now the heap is a data structure where you can put elements in. It will basically sort them on insertion. So you have a heap push where you push elements into our heap. It sorts them as you insert them, but it always keeps the smallest element at the top of the heap. So then you can pop that element off the top and you'll get the smallest element. And then you can insert a new element to the heap. It will resort, find the smallest element, put it at the top. You can just pop that out. So anytime you have sort of a shifting pool of elements where you might be adding or removing elements, and you always want to have the minimum element available, that is a perfect candidate for a heap type problem. So for this problem, we will be using a heap. So let's create our heap here. Now in Python, a heap is just a list, and we will use the heap queue library to do our push and our pop. There are 3 methods that we'll need to use. There's the heap queue. So the heap queue is the library. I'll put that here. So that's the library. So we'll have heap queue push, heap queue pop. I'll do, let's see, push, heap queue pop, and heap queue heapify. So what these will do, the heap queue heapify will just take a list and it will heapify it, meaning it will take this list and it will rearrange all the elements into a sorted order with the smallest element at the top of the heap. Heap push will take two arguments. It will take the heap you're pushing into and the element that you're pushing, and it will essentially insert that element into the heap, and it will reorder the heap to make sure that the minimum element is at the top of the heap. And heap pop will take just the heap itself, popping off the smallest value and returning it. So these are the pieces that we'll be using in this problem. All right. So here's my game plan. I will have two indices, a left index and a right index. The left index will indicate where are we in the array from the left start. So from the left side, we'll just have some left index that points to our current leftmost, or I should say rightmost of the left indices. It will just tell us where the left subset ends. Then I will also have a right index, and that will tell us where the right subset begins. So I'll have a left index that tells us where the left stops, and a right index that tells us where the right starts. So this way I will keep track of my two subsets, the subset on the left and the subset on the right. So that will start at, let's see, well, we have candidates in our left array, so we'll just start it at candidates. And our right index, well, that will be, let's see, the length of our costs minus our candidates. All right, now there's one edge case here that I'm not really handling for at the moment. Our left and our right indices might be overlapping. So for example, let's say we have 10 costs, but our left, or our number of candidates are 8. Well, 8 elements from the left will include everything except the last 2 elements, but 8 elements from the right will include everything but the first 2 elements. So there's this overlapping area where both the left subset and the right subset overlap and they have the same workers. This is something we don't really want. We don't want to have the same workers in our array. We'll have multiple copies of that worker. We don't want that. So we'll have to do a little bit of work to make sure that these don't overlap. Okay, so I have my left index, which tells me where the left subset ends, and I have my right index that tells me where my right subset starts. Now I need to fill the heap here. So let's see, for every index in range for our candidates, so we'll go through every candidate and we'll put each candidate into our heap. All right, so let's see the worker. Okay, so our worker here, we're just gonna call it worker. So that's gonna be costs at this index. So this is how much this worker costs. Now we're gonna put this worker into our heap. So heap.append worker. So this is putting our left subset into our heap. We also need to put our right subset into the heap. So I'll have a right index here, so that's j. And that's just going to be the length of our costs minus I. So this is basically coming from the right side and moving left. Maybe we'll call this left worker and right worker. So the right worker will be costs at index j. I'll call this left worker. So again, we're just building up our heap with all the workers that are in our candidate pool. Now, one problem with this approach so far that I see is this I, this index I, could be equal to this index j. And if that's the case, then we're putting the same worker into our heap more than once. So let's see. So we'll be putting our left worker in and then our right worker in. But if I and j are the same worker, then we've just duplicated a worker in our pool, which is not okay. We can't have the same worker chosen more than once. So we'll have to do some extra work here to make sure that we don't actually have duplicates. There are a couple different ways we can go about doing this. We could just check to see if I is equal to j, or if, I guess that's not true. If I is equal to j, that only occurs once as they pass each other, but it could be that j goes below I and I goes above j. So it's not just checking to see if I is equal to j here. We have to see if I is already in our heap. So for that, let's keep a visited, or yeah, I'll call it visited. So this is similar to something you might do in a graph type traversal. We're just going to keep track of which workers have already been visited, and that will just be a set. All right, so we are going to check to see if we've already put this worker into our heap. Now to do that, we actually need to keep track of what workers we've visited. So let's add this left worker. Actually, I can do it after the append, why not? Actually, before we add it to the heap, we need to check if we've already added it. All right, so if this left worker is already in visited, we don't want to add it to the heap. All right, if this left worker is not in visited, we'll add it to the heap. All right, and then j, we'll have the right worker, and we'll have to do the same thing here. All right, and now we do need to add these workers to our visited if we do add them to our heap. Wow, this is a lot of work just to create our heap. But I think it's going to work. So we've got our different workers. We'll grab them out of our costs. We'll put them in the heap. We'll make sure that we didn't already put them in the heap by checking that they're in visited or that they're not in visited. Then we'll add them to the visited list if we add them to our heap. Wow. All right. Once we've done all that, now we have our heap. It's got all the workers in our candidate pool. We need to do the first step in using our heap, and that's to heapify it. So we'll call heap q.heapify, and we'll pass in our heap. So this will basically just sort our heap into the heap sort order. This will keep the minimal value at the top. All right, so now that we have our heap, we can start going through and pulling workers from our heap and finding the best value we can. So one thing we'll need to keep track of is how many workers we've already pulled out. So I'll have a worker count, and we'll set it to 0. Now while our worker count is less than k, we'll grab a worker out of the heap. So for this, we'll use heap q.heap_pop, and we'll pass in our heap, which is just heap. So the heap q heap pop function will grab that first or minimal value out of the heap, and that returns our worker. Now our result will just be incremented by this worker. Awesome. This is working out really well so far. Next, now that we've pulled a worker out of our heap, we need to replace that worker with a new worker from our initial input list of costs here. So which worker do we replace them with? Well, it kind of depends where this worker came from. If this worker that we chose came from the left subset, then we'll need to replace that worker with someone else from the new left subset by advancing our left index, grabbing that worker and putting them into our left subset, or putting them into the heap at this point. If that worker came from the right subset, then we actually need to decrement our right index, grab that worker, put them into our heap, because they're basically part of the new right subset. Now the problem that we have here is we don't actually know where this worker came from. We just know how much they cost. We don't know the index where they came from. So we don't know if they came from the left subset or the right subset. So we actually need to keep track of more information than just their cost. We need to keep track of where this worker came from. We need their index. So for that, we need to change what we're storing. So in this case, our left worker is not just the cost anymore. It's going to be the cost and their index. So we'll make a tuple. Now a tuple is just a simple data structure, very similar to a list where you can have multiple values that are indexable, but the tuple is hashable. So that means we can throw this tuple into things like lists really easily. We can throw it into sets if we wanted to, which we will be doing here. So we will use a tuple. So the first element in our tuple will be our cost. So when the heap is doing its heap operations, It actually looks at the first element first. That's the primary sort element. If there's any ties, then it will look at the second element. So for us, that's exactly what we want. We want to sort by the cost first and then by the index later. Okay, so we'll have cost and then index. So now our left worker is now a tuple of cost and index. Same thing with our right worker down here. This will have to be the cost and its index, which is j. Okay, so then when we pop this value out, we don't just get the worker, we get the worker, well, I guess we get the worker, but the worker is not just the cost anymore. So we have to look at the worker's cost, add that to our result. Then we have to look at the worker's index to see if it came from the left or from the right subset. So the worker's index is stored in element 1. So if that is less than our left index, so this came out of our left subset, which means that we need to replace this worker with a worker in our new left subset, I guess. So the way to do that is just to put the worker at our left index into our heap. So for that, we do a heap q heap push. We pass in our heap as the first argument, and we pass in what we're pushing as our second argument. And so again, we need to sort of create this new worker. Maybe I'll create it here. New worker. So this new worker will be our costs at this left index and the left index itself. Remember, we have to store both the cost and the index in our tuple. So that's our new worker, and we will store our new worker. So that's if it's on the left side. We also do need to update our left index now. I'll do plus equals 1. Now, if it's not from the left subset, it's probably from the right subset. So we can do an else here. Let's see, do we do an else? We could try the else. I'm not 100% certain that this is right. I think there's one case that we're not considering here. Our left index and our right index, they'll be shifting. The left will be moving to the right one will be moving to the left. At some point, they will either be the same or they'll cross each other. So we might need to keep track of that up here. Let's do that. If the left index is greater than or equal to the right index, that means they've crossed over each other. We'll just continue. At this point, we don't have any more elements or we don't have any more workers we can add to our pool because their left index and the right index have merged. And at that point, all of those workers then are already in our heap. Okay. So back to our right here. So we've checked our worker. They look like they came from the left index up here, or the left subset up here, and we handled it. Now we have to handle the right subset. So this new worker, this is going to be, again, a tuple using the costs at the right index and the right index itself. Next, we'll actually add this worker to our heap. So that's, again, a heap q dot heap push, passing in our heap and this new worker. And then we decrement our right index. So our right index moves more to the left. All right. So one thing I didn't do, I'm not incrementing my worker count. As soon as we add a worker, we should be incrementing our worker count so we can actually make our way through this loop. So as soon as we pop the worker, actually, we can just increment this worker count because we know we are going to add them to this result. Okay, I think this is looking all right. So we'll go through, we'll pop the cheapest worker out, we'll add them to our result. Then if we can add more workers, or I guess I should say if we can't add more workers, we've actually merged our left and right candidate fields here, then they're all in our heap. We don't have any more workers to add, we'll just continue. If we have more workers that we can add, we'll actually check to see where this worker came from. If it came from the left subset, then we'll create our new worker from the left subset, which is basically the new worker at the current left index, push them onto the heap, and then we'll increment our left index. Same thing with our right. Okay. This actually equal to might not be right. It might actually have to be greater than. Let me see if that's true. I think we just need to do greater than, because if they're equal to, we might still want to add that equal to element or worker into our heap. Okay, let's give this a try. I'm not 100% convinced this will work, but let's try it. All right, index out of range. Oh, because this needs to be length of cost minus 1. So this length of cost will actually be greater than our actual last index, and this will start at 0. So yes, that was my mistake. Try that again. Okay, we pass one, but we don't pass the other. Looks like we are way too low. That's interesting. So this indicates that I'm probably counting the same, I think that's the key. I might be counting the same worker more than once. Let's do this. Let's just make sure that these are separate. All right, and we'll do a continue here just to make sure we don't actually fall through and do both of these. All right. Oh, and this is wrong. How did that happen? This should be minus equals. Index out of range. Ooh, dog. And this should be index 1. That's what happens when I rush. Okay, and that seems to pass. All right, just had to fix a couple silly mistakes there. So one, we do need to have two separate conditionals here. We do have to check that it's worker at index 1, not index I. My mistake. All right, let's submit this and see how it does. Wrong answer, but we do pass a lot of test cases. So that indicates to me there's probably an off by 1 somewhere in here. Oh boy. I'm off by 1. Where do you think we're off by 1? Well, we are going to K, we're keeping our heap, we're doing our count right, that seems to be right. Okay, we could have some mistakes in here. These all look good to me. Maybe it's something I did up here. So we start these, length minus candidates. I think my off by 1 is right here. Minus 1 minus our candidates. So we were including one of our candidates more than once, potentially. Silly mistakes. There we go. See, even I make silly mistakes sometimes. A lot of times, most of the time. All right, and we do pass. So let's see how we did. Oh, terribly. We only got 14% for runtime and 6% for memory. That is awful. All right, but I'm like way over time, and this is a lot of code. I am not going to do anything to improve this one. I would say try this one on your own. See if you can do better than a 14%, which I'm pretty sure you can. Once you do better than that, you can check in here, see how people do this one. You can jump up and see, oh, let's see, how did they do the best operating solution here? And it looks very similar to ours, except they've got this early out, which is pretty clever. So they calculate whether or not they even need to have two sides, two subsets, left or right. They just say if there's only one group of candidates, then we can just sort the candidates and we can return the first K of those candidates. So that's pretty clever. Otherwise, they actually do, this zip is basically merging, or I shouldn't say merging, it's, how do I describe this? I'm just going to skip describing it. All right. They're actually creating heap. They're doing the heapify. They're doing something very similar to what we're doing. They're a little bit smarter with how they do the pops and pushes. So we could actually do some of the same things they're doing here to make ours a little bit faster. So yeah, we're actually on the right track. All right, well that is it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.